Welcome back everyone. In this lecture we will define the normalizer of a subgroup and then see some basic properties of this notion. Okay, let's begin with setting up some notation. So as before, let us say G is a group and H is a subgroup. Okay, so we have this following question. So you can see that H is indeed normal in H. Okay, so this is something easy to see. Okay, as a subgroup of H, H is normal in H. So this actually motivates us to ask this following question. So what is this question? Is there any largest subgroup, let's say capital N, of G in which H is normal? Okay. So this question makes sense because this collection is actually non-trivial. There is this H which is a subgroup of G in which H is normal. So now we are looking for largest possible subgroup of capital G in which H is normal. Okay, of course, if H is to begin with normal subgroup, then the largest subgroup should be capital G. Okay. But note that if H is normal in G, then one of the characterization says for all G in capital N, then GH G inverse. This has to be exactly equal to H. Okay. So that means this motivates us to look for all elements of capital G that actually commutes with capital H. Okay. So indeed this motivates us to define this normalizer. Let me define it here of capital G in H. So what is the normalizer, which is denoted by Ng of H? Okay, it's pronounced as the normalizer of H in G. Okay, so this is, you take those elements in G such that which actually normalizes this capital H. So this GH G inverse should be in capital H. Okay, so this NGH is called the normalizer of H in G. Okay. So let us see some basic properties of this. So let me write it as proportion. Okay. So as I promised, okay, so let us fix the notation as before. H is a subgroup of G. So then this Ng of H, we can prove it is indeed a subgroup of G. Okay. So now once we prove that this Ng of H is a subgroup of G, then it is clear from the construction it must be the largest subgroup of G in which H is normal in it. Okay. So now obviously by definition H is normal inside Ng of H. Okay. And the third thing is, if there is another group which contains H and then H is normal in N, so then this N must be subgroup of this Ng of H. Okay. So these properties must be true. So again the second property is somewhat easy because that is by definition of the normalizer. The third part is also easy because that is something we verified here. Okay, that is again by definition. The only thing that remains to verify, Ng of H is indeed subgroup of G. Okay, for that let us start with two elements x, y inside Ng of H. So we want to prove that it is a subgroup. So that means x, y inverse inside Ng of H. Note that, so both x and y, they are coming from Ng of H. That means x H, x inverse is H and y H, y inverse is equal to H. But now by rewriting this equation, you can see that by conjugating, okay, y inverse on both sides. So I am just conjugating by y inverse y. So, you get this is exactly equal to y inverse hy. So, which is same as, okay, this y inverse y will get cancelled, this you get h. So, that means h is same as y inverse hy. So, that means y inverse is inside ng of h. Okay. So, that is already verified. So, now look at what will happen to xy inverse. Xy inverse, now you actually conjugate this with capital H. Okay. Then xy inverse capital H, xy inverse inverse. So, this is going to be equal to, so first you can rewrite this as follows: x y inverse h y and then x inverse. So, know that y inverse h y we proved it to be h. So, this is going to be exactly equal to x h x inverse, because y inverse h y is h, that is what we proved. So, now by definition of normalizer, x is in the normalizer. So, x h x inverse is also again h. So, this is going to be again h. So, that proves that x y inverse is again element of ng of h. Okay. So, that means ng of h is a subgroup of our G, and obviously by the definition of the normalizer, h is normal in ng of h and it is the largest subgroup in which h is being normal. Okay. So, one of the important thing is this normalizer need not be normal inside your group. Okay. So, note that. So, here is the warning. Okay. So, this normalizer of H need not be normal in G. Okay. So, there are cases for which this normalizer can be the group that you started with. Okay. So, it can happen that the normalizer of H is just H. Okay. For example, you can take the subgroup generated by 1 2 inside S 3. So, then you can easily see that this n H of S 3 n S 3 H is exactly H. Okay. So, this is actually case. So, these kind of subgroups for which the normalizer is itself, they are called self normalizing groups. Okay. So, if H equal to ng of H, then we say H is self normalizing. Okay. So, these groups are very, very important in, for example, in theory of semi-simple Lie groups. Okay. So, we will see, maybe I will add it in the assignment, some more examples of these self normalizing subgroups. So, in particularly this ng of H need not be even bigger than H, and definitely in that case if it is self normalizing it cannot be normal. Okay. So, similar to this normalizer, one can also define what is called centralizer of G. Okay. Centralizer of a subgroup. So, what is the centralizer of a subgroup? Okay. So, you look at all possible elements that are commuting with all elements of capital H. Okay. So, you take H again a subgroup of G. So, the centralizer which is denoted by Cg of H. So, this is those elements in G such that G commutes with all elements of capital H. Okay. So, basically you are collecting all possible elements of capital G that commutes with all elements of capital G, and it is easy to see that this centralizer is indeed subgroup of capital G. So, this is something I will leave it to you to verify. Okay. And then it is also easy to see that the centralizer is a subgroup inside the normalizer. Okay. If G commutes with all elements of H, then G definitely normalizes capital H. Okay. And it is not hard to see the centralizer of capital G is nothing but the center of the group. Okay. Similarly, if H is normal in G, then we know that the normalizer of H must be exactly equal to G. So these are all kind of characterizations in terms of this new phenomena, centralizers and normalizers. Again, given a subgroup, one can actually try to compute what will be the centralizers and so on. Okay. So maybe I will leave it to you to check. Okay. So here is some exercise, somewhat smaller exercise. Okay. Take S4 and then look at this subgroup which is generated by 1, 2, 3. Okay. And then find centralizer of this group. Okay. Find centralizer as well as normalizer. Okay. So this is something you can do for all groups. Okay. So let's move on. Now I would like to actually state some basic properties of group homomorphisms. Okay. Again, it will be used later in proving all isomorphism theorems corresponding to this group homomorphisms. Okay. So recall, so what is the definition of group homomorphism? Okay. So it is a map from one group to another group, okay, such that it should preserve the group laws, okay, phi of x y, okay. For example, so the product, let us say, happening on the left hand side, which let us say denoted by x star g y, then that should be exactly equal to phi of x star g dash phi of y, and this should be true for all x, y and g. Okay. So if you take the group G here and then the group G dash here, if you take two elements x and y, the product will lie somewhere here. Okay. The product is happening in G. Similarly, the images. So let us say x dash is what the image of this x, and then the y dash is the image of this y. So then the product of these two elements makes sense inside G dash, which is denoted by x dash y dash, and this x y should be mapped to this x dash y dash using this phi, okay, under this phi. So that is what we mean by the group laws are preserved by these maps. Okay. We have seen already many examples of these group homomorphisms. Okay. So now let us see some basic properties. Again, I will leave it to you to verify some of them. Okay. They are very easy, which I already stated before, but anyway I will restate it again. If you take the image of the identity element of capital G, that should be identity element inside G dash. Okay. And then if you take image of any a power n, that should be phi of a power n for all n in G. In particularly, phi of G inverse is exactly phi G inverse for all G in G. Okay. So now if you take, for some reason, if you know that order of G is finite, okay, so then order of this phi of G is also finite and it must divide order of G. Okay. So let me just verify this third thing. So suppose the order is finite, so let us call it n, which is the order of G. Then we know that G power n is identity, okay, identity inside G. So now if you apply phi, for this element, then it will map to phi of G because map is well defined. So, this is going to be identity G dash. Now, if you think about it, because n is being natural number, then you are taking the product of G n times, okay, then this can be rewritten as phi of G power n. Okay. So, G power n by definition G times G times G n number of times. Okay. If you apply phi, use this group law, then phi power G n will becomes the identity. Okay. But we have already seen that if some element is there and then whose power, some power is identity, then the order of that element should divide that power. Okay. So, that is what it says here. Okay. So, now look at this kernel which I already introduced, the kernel of phi, which is those x in G such that which is mapped to the identity element in G dash. Okay. So, this is something we proved, it is a normal subgroup inside G. Okay. So, now we also have another interesting group associated with this map phi, which is called the image, the image of phi. So, the image of phi, you collect all images of elements of capital G. Okay. And one can prove that this is again a subgroup of G dash. Okay. So, let us verify this. So, let us start with two elements, call it some, let us say A B inside image of phi. Okay. So, let this. So, this is a subset of G dash. Now, because A and B both are coming from the image, A can be written as some phi of x and B can be written as phi of y, okay, for some x in G and again y in G. So, now look at AB inverse. AB inverse is going to be phi of x, phi of y inverse. But we already know that phi of y inverse is nothing but phi of y inverse. Okay, that is what our statement 2 says. Okay. So, that means this AB inverse is exactly equal to phi of x times phi of y inverse. Now, using the group law, you see that this is exactly phi of x y inverse. Okay. So, that means AB inverse is nothing but phi of x y inverse. So, it is again image of some element. So, that means this is in the image of phi. So, that means image of phi is a subgroup of G dash. Okay. So, now you can actually generalize this. Okay. So, in both directions. So, that is what we want to understand right now. Okay. So, you have a map phi from G to G dash. Okay. So, here is G and then this is the map phi and then here is G dash. So, now what we can do, we can take a subgroup here, okay, call it H dash and look at its inverse image and then see what happens. Similarly, we can take a subgroup here, call it H and then look at its image and then see what happens. Okay. So, let us see. First start with the pre-image. Okay. Let H dash being a subgroup inside G dash. So, then look at the inverse image of H dash. So, this is called inverse image or the pre-image, inverse image of H dash. What it is, said theoretically, it is all those elements in G such that when you apply phi, that should be element in H dash. Okay. So, note that since identity is always there inside H dash, so that will imply that phi inverse of this identity, what it is exactly the kernel of phi. So, this should be subset of phi inverse of H dash. Okay. So, it is not some subset, it is containing kernel phi. So, now we will prove, okay, that phi inverse of this H dash is indeed a subgroup of G. Okay. If you start with the subgroup H dash, inside G dash, then look at its pre-image phi inverse of H dash, then this contains kernel and it is also a subgroup of G. Okay, that is what we are proving. So, let us verify this. Again, let us start with two elements, okay, A comma B from phi inverse of H dash. So, then in particularly phi of A and phi of B both will be element in H dash. Now, look at phi of A times phi of B inverse. This is again should be element of H dash because H dash being a subgroup. Okay. So, then you can see that this is exactly equal to phi of A, phi of B inverse, which is phi of A B inverse, which is inside H dash. So, that means A B inverse is inside phi inverse of H dash. Okay. So, that is what we wanted to prove that phi inverse of H dash is a subgroup. So, this proves that phi inverse of H dash is indeed a subgroup of G, and not only that, it contains the kernel of phi. Okay. So, now this motivates us to look for subgroups of G actually that contains kernel phi and then look at their image and what happens. Okay. So, let us look at. So, let us start with some subgroup and then see what happens. Okay. So, let us start with H being a just subgroup of G. I want to look at the image phi of H. What is phi of H? It is phi x, x in H. Note that, okay, so phi is a map from G to G dash, which is a group homomorphism. Okay. So, then if you can look at the restriction of this map to H, okay, because H is being a subgroup of G, I can restrict this to the subset. In particularly, it gives you a map from H to G dash. If phi is a group homomorphism, then it is easy to see phi restricted to H is also a group homomorphism. Okay. So, this is something easy to verify. I will leave it as exercise. In particularly, what will be the image of this H? So, this is going to be just image of phi restricted to H, but we have already seen that image of any image of this G is indeed subgroup, or image of any group homomorphism is a subgroup of G dash. In particularly, you can see that image of this phi restriction H, which is phi of H, is a subgroup of G dash. Okay. So, indeed what we proved, under this group homomorphisms, subgroups are mapped to subgroups and inverse of subgroups are also subgroups. Okay. This is what we proved. So, now we can actually have a map. Okay. So, this is the map that we are interested in understanding. So, let us fix this homomorphism phi from G to G dash. So, where you can have this collection A, this is those subgroups H of G containing the kernel as a subgroup. Okay. So, this is one collection, and then we are saying that there is a map, induced map from this to this another collection, which is all subgroups of G dash. H dash is subgroup of G dash. Okay. So, what is the map? The map is given by H goes to phi H. Okay. So, I will tell you in a minute, okay, why you want to restrict to only those subgroups that satisfy this property, because we want to actually somewhat build bijective correspondence. Okay. So, if you start with the subgroup here, then the inverse image has this property. That is why we are restricting to this particular collection on the left side. Okay. So, there is this natural field tilde map, that field tilde map maps H to phi H, and we claim that, okay, so this field tilde is actually a bijective correspondence. Okay. So, we already proved this is well defined, because if H is a subgroup, then phi of H is a subgroup, and if H equal to H dash, then phi of H equal to phi of H dash. So, it is a well defined map. So, we need to verify it is indeed surjective as well as injective. Surjective is again obvious, because if you start with H dash here, then look at phi inverse of H dash. So, then phi inverse of H dash is going to be H dash. Okay. So, that proves that phi is surjective. So, now only thing is remaining, phi is injective. So, to prove phi is injective, so let us look at H1 dash equal to H2 dash, then we need to prove that. So, the inverse image of these two are same. Okay. So, basically the inverse image is given by this, but why it is in this map to one unique element, because we have assumed that the kernel is contained in always in this. Okay. So, but by set theoretic language you can see that phi inverse of H1 dash is same as phi inverse of H2 dash. So, which is basically the pre-image. Okay. So, the inverse map is indeed given by, okay, the inverse of this is indeed given by H dash goes to phi inverse of H dash. So, once you restrict the collection to those subgroups that containing kernel, so then this inverse map is also well defined, okay, and it gives you the inverse of the phi tilde. So, that means phi tilde is indeed a bijective correspondence. So, there are this one can define this inclusion relation, okay, inside, okay, on both these subsets math call A and math call B. Okay. For example, if you take some H1 is contained in H2, then it is immediate that phi of H1 is contained in phi of H2. So, that means if you treat this as partially ordered set with respect to the partial order as inclusion, then this phi actually preserves that partial order. Okay. Similarly, the inverse map also will preserve, because if H1 dash is contained in H2 dash, then the inverse image of that is also contained in itself. Okay. So, this map phi tilde, okay, which is very interesting map, this is actually gives you the correspondence between the subgroups of G containing the kernel and the subgroups of this the image G dash, sorry. So, this H dash is inside G dash. Okay. So, I will stop here, and then in our next lecture we will actually see the important isomorphism theorems and their applications. Okay, I will stop here. Thanks.